take us right up until the final. Okay. Yes, sir.
I didn't do a review like yesterday at Form 1.
Am I going to do a review for? I think the short answer is no. I'm going to try. I'd rather do a review at the end of the class. And so if I spend a lecture doing a review for AM, then I may not get to be able to do that. And I think the time is best spent on that. If it works out that I have a little bit of time, I'll be happy to do it. But just play it by ear. Safe thing is don't count on it. Study hard, and don't need me. And then if you get it, great.
Is the final exam in this class comprehensive of everything?
The final exam in the class is absolutely comprehensive. And the questions on the homework questions could come from any assignment as well, any chapter as well. Okay.
How many will be on the final?
How many questions on the final? The final format will be very close to what we have, except it'll be worth 40%. So you can look for 4 to 5 problems instead of 3 to 4 problems, and at least one of those problems will be a homework problem. At least one of those problems is a homework problem. So if there may be 2, but I usually can come up with interesting problems on my own. Okay. All right. So we're going to continue to talk about FM today. And I thought it might be good just to do a quick review of what we did last time, and then a couple of examples, interesting examples that actually could unravel some stuff for us, a little bit more detail. So last time we were talking about almost exclusively about the bandwidth of the FM signal, and I guess when I posed this question, it was kind of who cares, and what's so hard about that? And so one of the takeaways from last class was the fact that we should care because we're going to put this over the airwaves or down a transmission line, and we're going to have, say, in a major market, we're going to have many FM radio stations, and we want to make sure we want to be able to understand how far apart they need to be carrier frequency wise. And amplitude modulation, it was fairly straightforward because the width of the baseband width of the signal was related directly to the carrier, to what you were sent out over the airwaves. FM was not that way. The way FM works is it's a very nonlinear operation. It's a cosine of a cosine or a cosine of a sum of cosines. And so you create all these frequencies, and it gets very, very unruly. And so given all that, how on earth do you approach the problem of what is an estimate for the bandwidth of the FM signal if the bandwidth can be said to be infinite or spread out across a very, very wide range? And so what we did was we took a look at the FM signal. We took a look at an FM signal, and we noted the form of the FM signal, which was some amplitude, a constant amplitude, which gives you a constant power. That has ramifications too. Cosine, and then the message signal is located inside the cosine, and so it's protected. It's in the envelope of the cosine. But now all of a sudden I'm taking a nonlinear transformation of the message signal. Okay, the cosine is a transcendental function. It's got a linear term, a quadratic term, a cubic term, and all the way up. And all those terms are distorting the message signal and creating more and more and more frequency components. But the other way to look at it is that the instantaneous frequency is proportional to the amplitude of the message signal. The instantaneous frequency is proportional to the amplitude of the message signal. So the higher the amplitude of the message signal, the higher this instantaneous frequency is. So the peak of this message signal will give me the peak frequency deviation. Okay. And so we can use that to track a range for the frequency And it's not quite that simple. It's not quite that simple because what we want to do is we want to slow down the signal a little bit, and we do that by sampling. And so we say, okay, mathematically what we have is we'll break up our overall M of P into a set of blocks. Each of these blocks is static, is constant for a duration, time capital T. that capital T is a little bit faster than the bandwidth. So 1 over 2b is that width, and that's the Nyquist rate. We'll go into that in more detail in a couple of lectures here. And then if that's the case, then we can write the instantaneous frequency at any function at any time, including the peak times, MP, and in this case, symmetric signal minus MP. Each one of these rectangles, or each one of these samples, transforms into an uncertainty of frequency. It transforms into a sinc function. And so I have a little bit of extra bandwidth that I have to contend with. So if I want my maximum instantaneous frequency and my minimum instantaneous frequency, then I've got my carrier frequency plus the peak plus a little bit more due to the Fourier transform of this rectangle pulse in time. So a little bit more here. So 3 terms making up the maximum frequency, 3 terms making up the minimum frequency. The bandwidth of the signal should be the max minus the min. Separate all that out. Don't worry too much about factors of 2s and so on like that. Separate all that out, and we get the bandwidth of the FM signal. And a very famous formula, the bandwidth of the FM signal is the baseband plus my deviation ratio beta plus a little bit more. And that's Carson's formula. Okay. The deviation ratio. These are interesting. I have a delta F, which is the KF times MP term. So the modulation index times the peak. That tells you the spread of the frequency in the carrier space. And then we compare that, delta F over B, we compare that to the baseband. And that's our deviation ratio beta. Okay? Yes, sir.
Should we know what KF is exactly?
Well, I'm going to answer that in a couple of ways, because I'm not sure the question was, do we need to know what KF is? KF is this constant that sits in here. Okay? So mathematically, it's the index on how much you stretch out your amplitude. So if your amplitude is 1 volt, how much more do you stretch it out in the frequency space or inside of this cosine term? So an attempt at a physical interpretation of KF. KF needs to be designed into your system. KF needs to be designed into your system. And so the more you spread out, the better performance you have. The more you get away from AM, the better performance you have, the higher KF, but also the more bandwidth that you use up. And so there's a trade-off between performance and economy of bandwidth. And for that reason, KF has to be a judgment call. You have to come up with it. But nowadays, if you're talking FM, it's a standard, and it's given. And it's usually given in terms of beta. If you go to my webpage, not the e-learning, but if you go to my webpage, there's the ITU standard from the 90s, I think, the most recent rev on FM. And you can see the frequency assignments. And it's that, from the frequency assignments, you get beta, and from beta, you get K sub F. To really answer your question, which I think is probably your intent, is somebody would have to tell you what KF is.
Okay.
but I want to get you thinking more like a practicing engineer instead of somebody who's just doing problems. But in fact, in the examples we'll do today, KF will be given as 50, for example. Okay. So anyway, this deviation ratio is important to the problem, and it's also an interesting and useful thing to think about intuitively. It is the spread of the frequency range given by the modulation to the spread of the frequency range of the original signal in baseband. Okay. Now, a different way to look at it, a different way to look at bandwidth, was to look at the tone modulation. So we know that M of t is a function of time, and therefore it can be written as a Fourier series. And so if we take one term of that Fourier series, we have a single cosine, which is our message signal. Okay, so we might ask ourselves, what is the simplest message signal I can put on? And that's a test pattern, a test tone, which is just a single cosine. So you're broadcasting one siren noise or just one key of a piano, for example, pressed down. So M of t is proportional, or alpha, times cosine omega mt. That A of t that we've been talking about, it's really just this term right here in the expression for the FM. It's just the integral of m of tau, and so we get this alpha over omega m sine of omega mt. We put that into our expression for the FM signal, and we can identify what beta is in terms of the kf, the magnitude of the peak of my message signal alpha, and then I'm dividing through by the frequency of the signal. That is in fact the capital B for the baseband signal. Okay. And when we do this, we simplify out our expression a little bit, and you see the deviation ratio, beta, popping up in there. And this piece is easy to deal with, but this piece is foreign to us. The trick in solving it, the math trick in looking at that, is to write that as a Fourier series. It is periodic in omega m, and so it makes sense to use omega m as our basis set. And if we do that, the coefficients, the Fourier coefficients, interestingly enough, can be written as a special function called the Bessel function. Okay? And the Bessel function is a very famous function for electrical engineers and for engineers in general, but particularly electrical engineers. And this probably is one of your first or second introductions to the Bessel function. So my plea is that you go back and you plot a bunch of these. Beta is your dependent variable. N is an index. 0, 1, 2, 3, 4, and so on. And that just tells you the Bessel, the first Bessel function, second Bessel function, and so on. And I'll talk a little bit more about this Fourier series in a little bit when we do an example here in just a moment. Now, if we accept that this is the prescription for this Fourier series, then we've solved the problem, and we can write the expression for the FM signal in terms of these coefficients. Okay? And the question is, how many of these terms in our Fourier series do we need to keep? But we see that we do get an infinite number of sidebands there. The formula, or when people look at this, when mathematicians look at this, they say, well, if n is greater than beta plus 1, then that Jn of beta is small. If you want to do a little bit more, if n is greater than beta plus 2, it's even more negligible. And so you can truncate this series where at n equals beta plus 1, in which case your bandwidth of your FM signal is exactly this, and I think I left out this B, baseband. Oh, nope, I don't. I have it at the end. Ha. There we go. And then the FM signal, the bandwidth of the FM signal is twice the bandwidth of the baseband multiplied by this beta plus 1, which is Carson's rule again. Okay, so last time we derived Carson's rule, we derived it in two different ways. And in both ways, we looked at the difference between the 1 and the 2 as a judgment call. Okay? Now hereafter, if you want to just memorize Carson's formula, probably you should go mainstream and just remember that it's 2b times beta plus 1. That seems to be the accepted form. But keep in mind where it came from, and it's not a hard and fast rule. It is exactly an estimate, and a good one. Okay, so I'm going to do two examples. Okay, this will be kind of boring, but that's okay. I think they're both of them will be will clear up some confusion, KFs, betas, and so on. Okay, I don't know if you can see that. There you go. I think this is an example in the book. I think it might be example 5.5, but I'm not sure.
That says 3000 T.
It does say 3000 T. And that says 2000 pi T. Okay. And this piece in here is my integral of my message signal. It's my integral of my message signal multiplied by k sub f. Okay, if this is FM. Okay. So we compare that to the form of the form of the FM signal that we transmit. And omega sub c is given at 100 kilohertz. Okay, so this list of things we might want to find: the power, the frequency deviation delta f, the deviation ratio beta, the phase deviation, and the bandwidth estimate. And the first thing we need to worry about is it's not explicitly asked there, but it's going to enter into a lot of our calculations, which is, for the message signal, what's my B? And if I look carefully at the message signal, I see that there's two sinusoids there. There's one at 2 pi, f equals 3000, or at hertz, 3000 over 2 pi. And there's also one at 2000 pi over 2 pi hertz. Okay? And this one here is faster than this one here. So in the Fourier series, I'm going to have two spikes. I'm going to have a spike at 2000 pi radians per second, and I'm going to have a spike at 3000 radians per second. And this one will be the outer one, and thus this one will be the biggest frequency of my baseband signal. Okay? So by inspection, I look at this frequency and I look at this frequency, and I say it's the bigger of the two, and that's capital B. Any questions about that? Is everyone really 100% confident that they can look at these two, at this signal here, and identify the capital B from it? I have a hand up.
You had like some square wave signal mixed in the.
I'm just saying. Look at these guys here.
Well, I mean, yeah.
So you're right. The question was, what if there was something else in there, and it would be and I think the example you gave me was a square wave, and the square wave is interesting because that has an infinite number of harmonics associated with it, right? And it has to have an infinite number of harmonics. Small digression. Because a square wave goes, theoretically, it goes from on to off to on in 0 nanoseconds, 0 picoseconds. And so the answer for that particular example would be a capital B equal to infinity. Saying it slowly doesn't make it go away. It's still harmful. And so that your example has gotten us into a world of hurt right off the bat. And so what we have to do is we'd have to use our judgment to first truncate based on rise time what signal we really had. Okay? Excellent question, excellent example. But getting back to this much more simple case, is everyone really comfortable with being able to identify capital B from that? It's one of those tricky questions that's easy once I tell you. But, okay, good. So,
Basically, B is
the biggest frequency at baseband that you have in your message signal. Basically, B is the frequency of the largest component of your Fourier series. Okay. So do you remember how we write this? If this is Hertz, this is capital B, and in this case, I've got two spikes. I guess this one's a little taller than the other. And this one's at 2,000 pi over 2 pi, and this one's at 3,000 over 2 pi. And so if I identify this guy, I compare these guys, the biggest extreme is this point, the biggest extreme is this point here.
And so why not the addition of the two?
I'm sorry, what?
Why not the addition of the two?
Is there a frequency component at the sum of the two frequencies? At baseband?
Yeah. I don't think I'm just overthinking it at this point.
It's okay. Thinking's good. Anyway, it's simple, but it's worth taking a look at. All right. Part A was the power. And here's my signal again. 10 times cosine of a nasty argument. What's my power for an FM signal like this?
The amplitude squared divided by 2.
Exactly. So, and we did that explicitly 2 lectures ago, I think. So the formulas for all that were built a couple lectures ago. So the frequency range, the frequency spread, is delta omega over 2 pi. And this delta omega comes from the limits of the instantaneous frequency. Remember how I said we always have to be ready to take the derivative of the very complicated stuff that finds its way into the argument of the cosine? Well, in this case here, all this stuff in here is theta of t. And so the instantaneous frequency is going to be the derivative of that. And I'm going to ask, where's that the biggest and where's that the smallest? And that's going to give me my delta omega. And delta omega will give me my frequency deviation. Okay. Now, one of the reasons that we wrote this as a 3000 and a 2000 pi was it makes it very clear that these are not harmonics of each other. Okay, and so asking, what is the minimum omega I and the maximum omega I? It becomes kind of difficult. But let's just be clever about it, or let's just be engineers about it, and say, well, the biggest I'm ever going to have to worry about, is if these guys two add up in phase, in which case this term and this term are both, the cosine of here and the cosine of here is both -1. Now that will never exactly happen, or you might have to wait a very, 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 very long time and get really, 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 really lucky for that to happen. But from an engineering system design perspective, it's the right answer. Okay? To say that when this and this are at its extreme minimum, these guys are going to add up to give me my minimum frequency. And similarly, when this is 1 and this is 1, I'll have the largest possible estimate for my maximum omega C.
Do you mean omega I for these minimum and maximum omega I, or is it?
Yes, I do. Okay. Sorry about that. Yep, minimum omega I and minimum instantaneous frequency, maximum. Subtract these guys, or subtract these all out, and get delta F. This is 12.4 kilohertz. Yes, I did. Oh, sorry. Yes, I'm sorry. Or 2 times 4 kilohertz. 2 times 12.4 kilohertz. Okay. So now, so what's the difference between 2 times 12.4 kilohertz and 12.4 kilohertz in terms of interpretation? What is the difference between those two in terms of interpretation?
Single side band.
Exactly right. So you have this instantaneous frequency, and it's wandering between -MP and positive MP. Okay, it's wandering between that. If I'm interested in the complete and total spread of this wander, then it's twice times 12.4 kilohertz. If I'm saying, okay, I have a symmetric signal, and I'm only if I'm speccing instead of the full bandwidth, the half bandwidth, which is a very reasonable convention, then I would spec it at 12.4 kilohertz.
So in this case, that forecast will be like the max minus n over 2?
Well, it always will be.
Yeah.
It always will be, because I'm swinging symmetrically. I'm swinging symmetrically from the minus cases to the plus cases for MPs. Okay. So yeah, so that's always going to be the case. And the reason I do this problem, and the reason we talk about that, is I think if you look in the book, it just gives you the 12.4 kilohertz, and there's no explanation. And so you'll be scratching your head and asking the question.
After it did the subtraction, it divided by 2.
Yeah. So we'll be explicit about that. And my point is not it's not one or the other. The point is to be really clear with your convention. Okay, it's to be really clear with the convention. I'm talking about the full width, or I'm talking about the half width. Okay? It's the communication side of electrical engineering. I don't mean comm systems side. I mean being able to talk to each other. All right, so deviation ratio is this beta. And this is equal to our answer from above divided by the bandwidth of my signal, capital B, the baseband bandwidth of my message signal. And picking the same reference, single sideband on both cases, single side on both cases, that's 12 kilohertz over 12.4 kilohertz over 1 kilohertz, which means a deviation factor of 12.4 for this case. And it's just to double check, beta is dimensionless, which is good because I'm going to shove it into this special function, this transcendental function, this Bessel function, and it doesn't want any units at all. Okay? So we're normalizing the two. The problem asks for a phase deviation, and we haven't really talked much about a phase deviation. We've talked about frequency deviation. That's the deviation of the instantaneous frequency. The phase deviation is the spread that this whole argument wanders through, right? Because this is, as I pointed out, you're taking the cosine of radians, a phase. So what is the angle? What is the phase angle that this guy is oscillating through in terms of radians? If the instantaneous frequency is oscillating through a certain range, then the accumulated radiance is also going through a range as well. So the phase deviation can be written as the radians collected by the omega CT plus an additional phase deviation here. And this is going to be 5 times the sine of 3000 t plus 10 times the cosine, sorry. Nope. Sine again of 2000 pi t. And again, what I'll do is I'll let that equal 1 and let that equal 1. And so the single side phase deviation will be 15 radians. Not quite 5 times around a unit circle. Okay. Oh, no, sorry. Not quite 2.5 times. Divided by 2 pi. Okay. 2 pi would be the complete unit circle phase. So you go 6, 12, and 1/2 of another circle, you get about 15. Plus 0.14, 0.14, and so on. Okay? So, slightly new concept. Bandwidth estimate. 2 times capital B plus beta plus, I'll use my derivation, 2 in there. So capital B, we found was a kilohertz. So 2 times a kilohertz. And then I have this beta plus 1 or beta plus 2. The beta we said was 12.4. So we can estimate our bandwidth of about 28 kilohertz. And that's 28 kilohertz on top of a carrier of 100 kilohertz. So that's a very, very, very spread spectrum. That spectrum is very, very spread out. To have a modulation of 12%, 28% of your carrier, that's very, very large. Okay? Now, you said it probably costs a lot, and all good things cost a lot of money. So that's always a trade-off. But I want to go back to something you said, which is how do we know what KF is? Okay, and one way to look into that is to take a look at this beta. Remember, this beta is proportional to KF, and so the design choice to get a beta equal to 12.4 gave us a KF that was quite high. We don't know what part of this or this is an amplitude or the KF of the signal, but that's a large beta. That's a large beta, and that leads to a large spectral efficiency or use of the spectrum. Okay. Let me do a slightly different example. Because I want to get the same thing in a couple of different ways. I'll still do an FM example. So let's say I have a carrier. Which is equal to 10 times cosine of omega c t. That's my carrier. This carrier is going to give me my amplitude of my signal, the broadcasted signal. And so again, that's going to be 10 squared over 2. And this will be my frequency. Let me say that my message signal which will equal 20 pi times t. Okay? So if I divide that by 2 pi, I get 10 hertz. So a very slow frequency on my bandwidth, on my baseband. Okay? And let's say that we're given KF is equal to 50. And determine, this is a tone modulation. And one thing we know about tone modulation is that we'll be able to write that as a summation of a Fourier series where the coefficients are the Bessel functions. The coefficients of the Fourier series for the FM signal are the Bessel functions of the arguments of the betas. So the question is, how many of those harmonics, how many terms of that Fourier series can we keep? So let's determine the number of harmonics needed to contain 99% of the modulated signal power. So, power of the carrier is just a squared over 2, which is 50. And if I take the integral of this and multiply by 50 and put that into my FM signal, so this is my expression for my FM signal. Here's my carrier, 2 pi fc. That's just omega c. Here's my amplitude. And this is my message signal. And this is the integral of that message signal as per the prescription for FM. And see my kf out there? And I'm being clunky with my 2 pi's, so you see exactly where they line up. So this term has units of radians, and this term will also have units of radians at the end of the day. And that's good because cosines like to take cosines of angles. Clean this up a little bit. So when I do the integral, I pull out a 1 over 20, do some dividing. And this guy right there is my beta. Has the amplitude of my message signal in it. It has my KF in it. And it has the result of the integration.
So beta equals 5.
Beta will equal 5. KF times the amplitude divided by the frequency at baseband, 10 hertz. Okay. Remember, our beta before was 12, so this is much smaller. I can also write for my Fourier series. Okay. So how many terms do I keep? So here's my Fourier series. Here's my e to the. Let me. This expression here from last time. The amplitude times the sum of j and of b, and here's my cosine term, my harmonics, omega c plus every n omega m. That's that guy there. And we know what some of these are. So finding the power of the Fourier series.
Can you shut it down and all?
I can. So what I want to do is I want to say, take this guy here. When I do my power of my Fourier series, I go term by term and I square them. I find the power term by term. So this cosine squared gives me a 1/2. This 10 gives me 100. This 10 squared gives me 100. So that's 100 over 2. And then I square each Fourier coefficient, which is j sub n squared, evaluated at beta equals 5. Term by term power calculation. So I'm going from n equals minus k to k. I want to know what k is, so that this is 99% times the power of my total launched signal. Find k. Okay. So this is equal to j0 squared at 5. This is going from minus k to k. So I'm going to go twice, n equals 1 to k. Jn squared of 5. And that has to be greater than 0.99. Let's divide by both sides by 50. So I'll create a table. Let me not cram myself in. So n I go to my Excel package, or I go to MATLAB, or maybe I have a really fancy calculator that has a Bessel function key on it. I bet there's an app for that. And I calculate, I find what each one of these are. So J0 of 5 has the value minus 0.1776. J1 of 5 has the value minus 0.32758. J2 of 5 has the value of 0.046565. And so on down the list. So you can get this from a CRC handbook of mathematics, or any number of tables that have tabulated Bessel functions, or they're stored inside of the Excel program, or recalculated inside of the Excel program, or so on and so forth. But that's where this column comes from. And from then, it's just we want to square those numbers. So we just square all those numbers, and then we keep a running total. So if I keep the 0th order term, I have 31% of my energy. 31% of the total amount of energy that's going is found in that. I'm sorry, 3%. I was looking, yeah, I'm so sorry. Yep, keep a running total. Sorry. Just did it again, didn't I? I'll just do that. So 3%, a small, tiny fraction, 3% of my energy is found in the 0th component, the 0th harmonic. I then add 21.5%. And that's the first two harmonics, north and south of that. And then I add another 0.004, another small contribution. And that gets me to about a quarter of my power. That gets me to about a quarter of my power. Yeah. I should be doing that twice. Did I not do that? My intent is to do it, but maybe I didn't.
Because then it'd be like 40-some% by this.
Oh, I'm sorry. I probably did it here. It's probably buried in there.
It's already doubled.
Yeah, it's probably doubled already in there. Double check. Yeah, by all means, you should write a little spreadsheet to double check this. I'm very comfortable with my answers on the final column. But you're right. This may be factor of 2 in there, except for the first one.
So why is the first one not double?
Okay.
Going back to Bessel functions?
Nope. It's a great question. It's going from minus infinity to infinity.
Yes.
And so you have a -1 and a +1, a -2 and a +2. But you only have 1 0.
Got it.
Okay? So nothing to do with the magic of Bessel functions at all. Everything to do with a simple Fourier series. And that's a great question, because it's, when you're learning something new and you're confused, you don't know where that question is going to come. Is it at the new confusing part, or is it the old stuff? And so that's a good question. All right, now if I keep adding this up here, this doubles my contribution, 0.516697. Another whopping addition. Another one that gets me pretty good shape. And the final one puts me over my spec. I've done it. So I need to keep 6 of my harmonics. And in fact, if you go back and you say, Carson's rule is beta plus 1. Carson's rule wants the bandwidth is the estimate that goes as beta plus 1. And beta was 5. So we see that Carson's rule is equivalent of saying, I want to keep 99% of my energy in my harmonics, of my tone modulation. Okay. That's what Carson's. That example should tie up both ways of looking at bandwidths. Okay.
So going back to one of the previous problems where it was 12.45 equals beta, right?
Yes.
In that case, K would have to equal 13?
Okay, well, let's go. I'm sorry. In the previous example, we found that beta was equal to 12.4. And so we estimated the bandwidth from 12.4 plus 2. And so that you're right, that is exactly, the interpretation of that is how many harmonics you need for 99%, and you would need to keep 13 harmonics. Okay? And it would be great if you wrote a little table for that as well, to prove that. Okay? All right. Any questions on those examples?
So it's 13 harmonics, right?
For the other one, it was 12.4, so you might keep one or two extra. So 12, 13, 14 harmonics. It's a really good, if you go ahead and reproduce that table in Excel, you'll be able to check everything, apply it to that new, the example number 1, and show that. But basically, that's the interpretation of Carson's rule. All right. Let's see. Now we've got some time. I'll go start on this subject, and I'll probably repeat myself next time, but that's okay because it's a little subtle. Okay, so the statement I'm going to make and explore a little bit is that FM and PM, angle modulation, exponential modulation, is insensitive to distortion from nonlinearities. And if you remember the way that Armstrong chose to generate FM, he first did narrowband FM, and then he was looking for the biggest nonlinearity he could find, biggest nonlinear element he could find, and he just drew that signal right into that to generate all those additional harmonics on purpose. And if that's his technique for generating it, you can imagine that once you've generated it, a little bit more or less isn't going to matter too much. Okay? Another way to think about it is your power is constant. So if you're sending it through a device or a channel that's nonlinear, and you're maintaining a constant power, the nonlinearity doesn't affect one bit what goes on. Okay? On the other hand, for AM, depending on the magnitude of the message signal itself, sometimes at any instant, I might be transmitting a high power. In fact, in some instances, I might be transmitting no power for a mu equal to 1. So I have a whole range of powers going through my nonlinear device. So yeah, there's going to be some distortion on top of that. Okay? So I'm going to look at a channel. And that channel is going to be nonlinear. So I'm going to say that my y of t, my output, is going to be my input x of t. And I'll have a linear term. And I'll have a quadratic term. And I'll keep a cubic term too. So I have a linear response. That's the linear term. And these two will be examples of nonlinear terms. So let's think about this. Let's think about this physically before we put pen to paper and do some math. The channel is nonlinear. So that means the more power I send down the channel, the response changes. The response changes in, quadratically and then cubically with the strength of the field that I send through. Vacuum isn't really like that. Air really isn't like that. I suppose you could imagine a cloud, a rain cloud, and if you beamed enough power through it, you could probably dry it out and make it go away. But that's a pretty extreme example of a nonlinear atmosphere propagation. I'm sure there's some military radars that can fry birds, and so therefore can probably fry clouds as well. And in fact, I've seen papers where for free space laser communications, one, say on a say a battlefield where there's a lot of soots and dust and everything, you take a big old hairy CO2 laser and you blast a hole through it and then you transmit behind it. But where this really comes up on a day-by-day basis is in the fiber optic links that link together cities, link together continents. By far the much bigger dollar-wise investment than even wireless. We see wireless. We see wireless because we carry cell phones in our pocket, and so we tend to think of the communication infrastructure as wireless. But more or less on average over the last 10, 15 years, for every dollar that was spent on the fringes of the wireless, $2 to $4 was spent on the optics background, the wireline background that links all of everything together. So the infrastructure, the glass infrastructure is much more expensive or much more present on a cost basis than the wireless basis. It's not either or. You need both to perfectly solve the problem of the fringe and the core. But think about what you're doing with that fiber. It's a waveguide. You're pumping electromagnetic energy, power, down a glass strand. The core, where all the action is 9 microns. It's 9 microns. And you're launching an average power of about a milliwatt on every one of about 160 channels, 160 different lasers. And you're focusing all that power, that milliwatt of power, not much power, a milliwatt, but you're focusing it to a circle that has a diameter of 9 microns. And then you're keeping it there for 9 megameters, for 9,000 kilometers. And that's an incredibly long interaction length. So glass, being pretty transparent, you don't think of that glass window back there as being nonlinear. It doesn't grow dark when I send too much light through it. But it does happen if you're in extreme conditions for 9 micron spot size times megameters of length. And then what happens is in the glass, the field strengths associated with the light, the electric fields, volts per meter, remember that's a force, that gives you a force. That force starts to compress the silicon dioxide chains that make up the glass. The electrostatic force, the electromagnetic force, starts to compress and expand. The index of refraction is going to change as a function of that force. Higher densities and lower densities. And that's going to wreak havoc with your signal. And so in those situations, nonlinearities are the dominant impairment for fiber systems, and basically lead to the rule of thumb of don't launch more than a milliwatt into your fiber, unless you really, really, really know what you're doing with respect to nonlinearities. Now, if you broke down and transmitted it, if this is true, FM and PM is insensitive to distortion from nonlinearities. If you broke down and you transmitted everything as an FM signal, you'd probably be mostly always linear. Probably. However, it's super expensive to do that. And so people live with amplitude modulation in fibers. And they learn to work around the impairments. And so this example here is very close to what you would find to work out, the impairments in a fiber optic channel. You have an index of refraction that's constant, a term that varies quadratically, and another term that varies cubically with the field strength of the signal. Okay. So this block diagram looks very mathematical and very abstract, and yet it's exactly what's going on in the fiber plant. Okay. All right. Now, for the AM case, we're going to have x of t is equal to m of t times cosine of omega t. And for the FM case, for the FM and PM case, I'm going to have a constant amplitude out front, and there's my message signal floating around in there. It's either for the phase modulation or for the frequency modulation case. So in this case, my amplitude is varying all over the map. In this case, my amplitude is constant. In this case, my envelope, my carrier frequency is just going. In this case, the inside of my carrier frequency is varying all over the map. There's a trig identity for the cosine squared, which I think we're almost remembering. Look at Appendix E. We need both the quadratic and the cubic. And there's the trig identity for the cubic. So my output y of t is going to be a1 times the linear term plus a2 times the quadratic term plus a3 times the cubic term. Here's the linear term, the quadratic term, and the cubic term. And notice that when I go to the cubic term, one of my sidebands is down at the fundamental. We could low-pass filter this guy out. We could low-pass filter this guy out. But this guy sends you the harmonic right back on top of baseband. Right back on top of the linear response. And that's what's going on that guy right there.
So you can say it's strength. So you,
Well, let's take a look. Let's take a look. I'm just going to collect the terms. So what I've done is I've just collected the harmonics. The information is replicated over higher and higher frequencies. So this is just like the Armstrong method. If you don't like these terms, then the observation is absolutely correct. The cubic term helps. The strength of the signal and gives no distortion. Okay. Let me quickly contrast that with the AM case. Here's what comes out for my AM signal, the linear term,